I run the engineering program at Mount San Antonio College. We've been doing Battlebots for, oh boy, since season 2 of ABC, so for quite a number of years. And I thought I'd talk a little bit about what Battlebots has done for our program and how it's helped us bring students in. And I think one of the things I want to start with is we're a community college. And I'll tell you what, folks, if you don't know a lot about community colleges, I'm going to tell you a little bit about community colleges. Community colleges are where places people go where they want to go to work, they want to get a job, they want to get skills that are going to put them into the workforce, make them useful. And so there's a lot of people out there who don't really know what they want to do. They can find themselves. So we have a big engineering technology program, a big pre-engineering program, and we're really trying to fill this gap. There are a tremendous number of engineers out there, but there aren't people to actually do the work a lot of times. So that's what we do. We put people into the position where they have the skills they need to actually do the work. So I've got 3 of my students here today, Ryan, Misael, and Zach. They're going to talk a little bit about what they were doing this summer. Honestly, what they were doing was building Happy Cat, or the robot some of you guys have had a chance to see. And we tried to do a couple new things on the robot. Hey, we got some people coming over to listen to us. Fantastic. And my expert pointer. All right, so Zach's going to talk a little bit about magnets and why we did magnets, what we did with magnets, some of the different things that we looked at, and what our solution ended up being. All right, Zach, I'm going to hand it over to you.
Hey folks, so magnets. So you're probably asking, why are we using magnets on our robot? And the core reason why we're doing it is to get downforce. Now, essentially what downforce is the force applied to you in a downward direction. So think of gravity. So when I jump up like that, the reason why I come back down is downforce. It's the force of gravity. So ideally what we want is something greater than the force of gravity on our robot for a lot of reasons. One, it squishes down our wheels so we get more traction. 2, so then when another robot hits us, it's hard to hit us because instead of being 250 pounds, it's like we're 500 pounds. So it's much harder to hit us. So that's the reasons why we want magnets. Now, how we are doing magnets. So we looked at a couple different approaches. One, we looked at something called a Hallback array. Essentially what it is it's an array of magnets in a certain order and position. All that's fancy stuff. And the reason why you want to use a Hallback array is because it's great in one direction and it focuses your force towards one direction, which is exactly what we want. Because we only want magnets down. Yeah, that's all we want. Because if we're going up, then it's going up into the frame, which does nothing for us. Into the sides, that does nothing for us. Hallback arrays are good, but not the best solution. What we found is that you could actually get more magnetic force by putting magnets in a north-south position. So it's like you have your magnet, south-facing magnet, then a north-facing magnet, then a south-facing magnet. That'll give you more force than a Hallback array. But the second thing we're doing is we're putting a metal casing around our magnets so that it forces our magnet, it forces our magnetic field into one direction. So you get the advantage of being able to only having magnetic force in one direction, and you're getting a lot of downforce.
We're going to do a quick demonstration for you guys here. So Zach's going to talk about what I'm doing, bring the magnet around, and hopefully there's some metal on these risers, right? All right, so here we go. I'm going to bring it around. Zach, you tell them what's going to happen with this. We're going to do one side, then the other.
So on the side facing...
Are you ready? You're a pretty strong guy, right? Okay.
So the side exposed is going to have a lot more force than having the side in the back.
They're pretty good, right? All right. Now we're going to flip it around. All right, we're going to get a couple more people here. All right, so you saw he just pulled that right off, right? Come on down here, see if you can pull it off. Let's see if you can pull it off here. He's pulling. Oh, yeah. All right. Oh, man, you made that look easy. Holy smokes. All right. anything else you want to say about magnets? All right, so folks, we ran 12 of these on the robot. I don't know, how hard were you pulling there, you think, Luke? Probably 40, 50 pounds? Yeah. So at 0 separation distance, we get about 50 pounds out of these magnets, times 12 of them. That's 600 pounds. Too much, Andy, we would agree. But we're not at 0 separation, right? We actually space them about a 1/16 of an inch, right? For those of you that are European, that's about 2 millimeters, right? And yeah, so about 2 millimeters above the surface. And we obviously don't want to be resting on the magnets because then the robot doesn't drive right. We'd say it's high centered. And one of the special features of Andy's floor here is he welded a bunch of seams in there. And so we kept having to move the magnets higher and higher and higher as it went on. But that's a learning experience for us. And honestly, folks, coming here is a big learning experience for us. We get to test all of these things on our robot before we go and do Battlebots Season 7. Right, that's coming up soon. All right, so Zach talked to you a little bit about magnets. And I told you guys that, our magnetic force is a function of distance. So the further our magnets are separated from the floor, the less force we're going to get. And Luke said about 50 pounds trying to pull that thing off. This young gentleman was pulling as hard as he could, right? But I made it easy for you, didn't I? Right, all right. So, all right, now Ryan here, he's going to talk a little bit about what we did with some innovations with motors, and one of the things that we've done and kind of how things are changed. So Ryan, why don't you talk a little bit about motors for us?
Hello. So previous Mad Catters ran six of these little tiny motors called 6374. It looks like about half of a soda can, roughly. Okay. Can you hear me now? Okay. So previous Mad Catters ran 7 of these tiny 6374s. They look a little like soda cans almost. So with that, they're 3,000 watts each. So with the new motors we found, which are these giant can-looking things, they look like the 16 ounces you get at the store, which is pretty cool. These are 10,000 watts, almost a 3 times increase in motor power. The only downside, they're sensorless, so you don't actually track what position we are. So with our new drive system, we're testing out these ESCs in a special mode called VSS and HFI technologies. So in our current config, we're running 4 of these instead of 6 of these tiny small cans, which is a lot more simpler. We're also running almost a 10 times reduction, which is a lot more reduction than our previous motors. And if you wanted to come, you can also grab one of these. These things are heavy. These are very heavy.
Pass the motor around here, folks.
They are also very expensive.
All right, so folks, to be fair, if you get a chance to go and look at some of the robots, and I highly encourage you guys to go, get a pit pass, go back in the pits. All right, you can tour and see all the insides of these robots. There's been kind of 2 generations of technology. Just in my time doing this, okay, maybe that's longer than I'll admit, but we used to run brushed motors, right? And brushed motors have little brushes that attach a contactor. Those are what switch the direction of the current inside the motor. And brushless motors actually have 3 different phases that are alternatingly energized to twist the shaft around. But there's nothing contacting the shaft the way there is in a brushed motor. So you have a lot less friction, the motor can be a lot more efficient. These motors right here are roughly 90% efficient. Our old brushed motors were between 65 and 70% efficient. And what that means is heat, right? If your motor is only, let's say, 2/3 efficient, that means 1/3 of the power you put into the motor is going into heat. And if we're putting in 1,000 watts, 2,000 watts into a motor, we're generating 300, 600 watts of heat. That's a tremendous amount. And sometimes you'll see the robots catch fire during the match, and it's not like something wrong, it's just the motor got really, really hot. If you go from 2/3 efficient to 90% efficient, you've dropped the amount of heat you're producing by a tremendous amount. And I'll just tell you guys, in the robot this year, we've got 4 10,000 watt motors, so 40,000 watts on drive roughly, 40,000 watts. I'm going to convert that into horsepower, just for your sense. 57 horsepower in a 250-pound thing. Now think about a car. Okay, think about a race car, right? If you had 570 horsepower in a 2,500-pound car, that would be pretty freaking amazing. And that's what this robot is doing. So it's part of the reason for the magnets that Zach was talking about is we want to put that power to the ground, right? There's no point in having all that power if you just spin your tires, right? You saw us do a lot of tire spinning if you've seen our matches today. So that's something we're certainly working on. And you play with different tire compounds, trying to get really sticky tires. You heat them up before the match. You heat them up during the match, right? And one of the things that Ryan does have in his other hand there is that's the arm lifter gearbox. Some of you guys have seen our arm going up and down. It's really a different thing. The wheels have to spin really, really fast. But with the arm, it actually moves pretty slow. Now the motor is spinning at about 6,000 RPM and the arm is moving this fast. Well, that means you've got a tremendous amount of reduction, right? We have about 128 to 1 reduction, which means the sprocket that's driving the arm is moving 1/28 the speed that the motor is turning. And that's because we want a lot of torque. We want to be able to lift any robot out there, right? With just that one little motor. So that's a custom gearbox that was designed by students a couple years ago. This year the students designed a brand new in-runner gearbox for these new bigger motors, and that's how we get the power from the motor to the wheels. And so, you know, I'll say there's a bunch of other problems that we've had to deal with. Wheel design is another one. If you watch our matches, you notice kind of the wheels are going everywhere. So you can't just go buy these wheels off the shelf. Everything has to be designed. So the students design them in CAD, manufacture them in our shop, put them on the robot, and then we're thankful that these guys bring a big arena for us to test them in. All right. We also, honestly, the whole robot, this version of Happy Catter was built. We started on July 4th. We arrived here July 14th, so that was about a 10-day build for us. Many hours in the shop. But really, the only way you learn stuff is to get your hands dirty. And I would encourage all of you, those of you that aren't already running robots, Luke, this is a tremendous thing to do. It's a lot of fun for kids. You're ready to start your first robot. All right. So I encourage you guys. There's a tremendous amount you learn building these things. You can start out in the inset classes and move up to bigger and bigger robots, eventually to the heavyweights. But it's better to start small when you can still lift them by yourself, right? And also they're maybe a little less expensive. Your parents would appreciate that. All right, so at this point, the last thing I'm going to talk about is speed controllers. We've got to have a way to tell the motor to turn forward or backwards. Now, back in the old days of brushed motors, all you had to do was connect a voltage to the motor and it would turn. Well, modern brushless motors require a tremendous amount more. You actually have to time the motor. You have to energize the phase of the motor in the right sequence. 1, 2, 3, 1, 2, 3 to kind of kick the motor around. And you have to go faster and faster and faster as the motor moves. The other thing that's the really hard problem is the zero crossing. You're going forward and then you're going backwards, and keeping track of that rotor position is a really difficult challenge. There's two ways they do that. One of them is called back EMF. EMF stands for electromotive force, and basically anytime you have a magnet moving in a coil, it produces a little bit of a voltage. You can detect that and use that to determine kind of how fast your motor's moving and where it is. That requires the motor to be moving. But one of the hardest challenges, especially everybody who runs robots knows this, is getting things to start, right? Getting your weapon to start. Once it starts, you're good, right? But it's starting from zero. At zero, you don't have any EMF information because nothing's moving. So we use something called saliency. And saliency is a measure of the inductance of the motor. Basically, it's mechanical properties that we can measure electrically. And by measuring the saliency, we can determine the rotor position. But this is a little bit of a trick. What we do is we actually inject a very high frequency. Now, what's a high frequency? Well, you know, frequency is just like pitch. This is a low frequency. This is a high frequency. So we inject a high frequency. You'll actually hear our robot go beep. It'll make like a whining sound. And what we're doing is we're injecting this high frequency and measuring the feedback, measuring the saliency of the motor due to that high frequency. And we can very quickly determine the position and use that to start our motor. So that's been one of our big research projects. We've made custom speed controllers using this principle, and we've been testing them so far this time. And I'll say, folks, it's great for us when the thing that's failing is the tires, and all the hard stuff like speed controllers and motors is all working fine. So that's a big victory for us. So folks, we're Mount San Antonio College. I would encourage all of you guys two things. First of all, if you are interested in technology or just trying to figure out what you want to do, community college is a great place to start. You can sample just about anything there. And also, folks, you know, Combat Robots is a great way you can start. My daughter started when she was 8, so she's, you know, you're already a couple of years older than her. And, you know, you can start really young, and it's a tremendous way to learn, get your hands on things, learn a lot of tangible skills, and just decide what you want to do with your life, okay? All right, anybody have any questions for us? We're going to open it up for questions. Who's got a question? You got a question, all right.
So my question was, do you ever have any interference issues with the magnets and the motors and the radio and all that stuff? And if so, what do you do about it?
All right, that's a great question. So honestly, interference has been something that's plagued robots for a while. When we first started, we were using a frequency modulation scheme, so FM radios. We actually used crystals to set the frequency of the radios we were using. Boy, I was glad when that went away. And now we're using, some teams are still using, it's all 2.4 gigahertz. And the problem with 2.4 gigahertz, it's everywhere in here, right? We use either a dual spectrum or spread spectrum process. And yes is the short answer. The thing is, one of the things we experimented with, and the Ryzen team is actually running, we tried and it didn't work. But they're running something called LoRa, which is an error correcting encoded system for doing this. It's one of these things that's this open source developed thing. So, you know, we ran that at our last event, had some issues, and we've gone back to using some standard hobby things that are true spread spectrum. They've actually got a diversity antenna. They're constantly, one antenna is locked in, the other one is looking to see where there's an open channel, and it moves around to kind of where there's the least interference. We're doing everything we can on this. You know, with the magnets, Zach talked about the Hayback arrays and, you know, minimize. It turns out, you saw from the example I did with the two sides. Now, if you don't shield your magnets, you are absolutely causing yourself problems, right? Some people just stick magnets in their robot and then they wonder why things aren't working the way they're supposed to be, right? So magnetic shielding is really important. It's certainly something we see, but honestly, magnets is penetrating all the weight classes, right? They're, you know, and you see them in the insects, and in the heavyweights, it's just everything is heavier. But it's something that's really changing the game, and really different events tend to treat it differently. I know, like I think our Beetleweight arena is wood, right? And then this arena is steel. So in Beetleweights, they've kind of removed that from the equation. And, you know, the events are still dramatic and exciting, but magnets really let you get, you know, we were aiming for 1.3 Gs of acceleration here. And we weren't getting there at this event, but that's, again, it's a learning process for us. The wheels tear off before we get there. You've seen us lose wheels pretty constantly. But that's a good sign, right? If everything's too strong for the wheels, we're on the right track. All right, any other questions? You've got a question? Come on up.
What is your, like, power source here? Like, what type of, like, battery are you using?
All right, that's a great question about batteries. So, you know, I'll tell you what, back when I was first starting this, we used car batteries, all right, SLA lead acid batteries, and they were heavy and full of nasty chemicals. All right, everything's always full of nasty chemicals, that doesn't change. But what's really changed is all but one robot at this event is running lithium polymer or lithium iron batteries. They're the same batteries. Actually, we were running Tesla batteries for a little while. We had some Tesla batteries. But yeah, we're running running lithium batteries. They're very high energy density and lightweight. That's why we all run them. With the exception of Avalanche. Avalanche is running nickel cadmium batteries, which were state of the art in 2011, right? But really in the last 10, 11, since you've been born, the batteries have really changed, right? And just to give you guys a sense of scale, I told you guys the horsepower, 57 horsepower on drive, right? Our weapon is only, like 35 horsepower. Yeah, only, right? But you got to have a lot of batteries. We put roughly 20 pounds of batteries. We're running the robot at 60 volts. And for the people running smaller robots, this all sounds crazy, right? 60 volts. We're running roughly 20 amp hours, and we run them to like everything is at 20, 30. Well, it depends on how long the match is. The matches here, we're not running, kind of full out crazy. But in Battlebots, those packs are down at 20% at the end. So we're using a tremendous amount of power because we're using a tremendous amount of power, right? That's part of the game. All right. Any last questions? All right. Are you guys ready to see some fights? We're going to start some fights up pretty soon here. All right. So in about 7 or 8 minutes, we're going to have some fights coming back in the arena. So folks, go get some water, use the restroom, and then we'll round everybody back up. Thank you guys. All right.
Wonderful presentation, Mark.